Hi guys. So today we are going to do something that you did many times in Algebra 2, and that is find the inverse of a function. So if you remember from Algebra 2, the way you find an inverse is you switch the x and the y. Okay? You do not make anything negative, you do not make anything a fraction. All you do is switch x and y. So to find the inverse of this first function, f of x means y. So to switch them, that would be x equals 2y plus 4. So then from there, we would go ahead and solve for y. So I would subtract 4 and divide by 2. Now when I divide by 2, I'm dividing this whole thing by 2, which means I'm dividing each individual number by 2. So I can rewrite this as 1/2 x minus 2. Now the notation that we use for inverse is f with a little -1 as an exponent of x. So that's the notation for inverse. So this is the inverse of the function 2x plus 4. So what I'm going to do now is I'm going to graph both of these lines. So I'm going to graph 1/2 x minus 2. So y-intercept of -2, slope of 1/2, so up 1 over 2. And that is my inverse. Then I'm going to graph the original. So the original has a y-intercept of 4 and a slope of 2. Oops, missed that one. There we go. And what you may notice, if you don't remember, again, from Algebra 2, is that these graphs are reflections over the line y equals x. Something else that you'll notice about these graphs are that the x and the y coordinates are flipped, which makes sense because that's what happened with how we found the function. We switched x and y. But let's look at some of these points, for example. This is the point 1, 6. So if I switch the x and the y, I get the point 6, 1. This down here is the point 0, -2. If I switch the x and the y, then I get the point -2, 0. If you notice both graphs go through the point -4, -4, that's because if you switch the x and the y, it's the same point. So that's the other way that we find an inverse, okay? You switch x and y, whether it's a graph or an equation. So now let's try this for an equation. All right, so I'll take this point right here. That point is -3, 0. I'm going to flip the x and the y. So that becomes 0, -3. All right, now let me try another point in this graph. Okay, on the original function, that was 0, 3. If I flip x and y, it's 3, 0. Okay, again, the original graph was 3, 0. If I switch x and y, it's 0, 3. All right, so now let's look and see if the inverse is a function. So no, the inverse is not a function. We'll come back to that in a little bit. All right, let's find the domain and range of the original. So the original function's domain, those are the x values. Those go from -3 to 3. It touches both points, so we need brackets. The original function's range, bottom to top, that's 0 to 3. So it needs brackets as well. Now let's write the domain and range of the red graph, the inverse. Well, the domain, left to right, is from 0 to 3. It touches both of those points, so we need brackets. Range, bottom to top, -3 to 3, both of which need brackets. And what you may notice, or maybe even remember from Algebra 2, is that those two things are flipped. And if you really think about it, it makes sense. Domain are my x's. So if the inverse switches the x's and the y's, then the x's become the y's. All right, so if you feel comfortable, pause the video, try this next one. All right, so let's go ahead and graph the inverse. So this point is 0, 5. Switch x and y, and I get 5, 0. That point right there is 1, 4. So switch x and y, and I'm graphing 4, 1. And then I'm going to get one more point to make this a little bit easier. I'll use this point over here. That point is 9, 2. So if I switch x and y, it'll be 2, 9. And that's my graph. In this case, yes, the inverse is a function. It passes the vertical line test. All right, let's write our domain of the original. So from left to right, we'll assume there's an arrow there. So that would be from 0 to infinity. Range, we go bottom to top. And again, we're going to assume there's an arrow there. So we're going to say from -infinity to 5, it touches 5, so it gets a bracket. All right, domain of the original left to right, negative infinity to 5 with a bracket. Range is bottom to top, which is 0 to infinity with a bracket. And again, you'll notice they're flipped. All right, so let's find a few more inverses algebraically. Now, this note here about inverse of a square root graph, if you noticed, this is a little bit past what we're doing today, but again, a good review from Algebra 2 for you guys if you remember. The original was a square root function. What we got as a result kind of looks like a quadratic, but it's not a whole quadratic, which means that answer actually has a domain restriction. But that's a little bit past what we're doing for today. Okay, so let's just solve algebraically to find the inverse. Okay, so what we do is we switch x and y. Okay, so hopefully by now you're starting to see that pattern. F of x means y. So if I switch x and y, I would do x equals the cube root of 2y plus 7, and then I'm going to solve for y. So subtract 7. To get rid of that cube root, I would cube both sides. And remember, that does not mean I cube the individual values. I'm going to keep it in those parentheses because that's how it would look if I were to graph it. Then my last thing would be to divide by 2. So if I want, I could leave it like that, or I could write this as 1/2 x minus 7 cubed. And remember that notation, it's f with a little -1 of x. All right, let's look at another. Switch x and y and solve for y. So x equals y squared plus 4. So minus 4. And to get y by itself, I would have to square root it. So I'll square root the right and I'll square root the left. So I end up with the square root of x minus 4 equals y. Now I'm going to use that right notation, so f little -1 of x equals the square root of x minus 4. Now one thing you'll notice on the original, again, this is a little bit past where we're going for today, but it says that x is greater than or equal to 0. What that means is you're not graphing the whole quadratic. That's what allows just this square root function to be your answer. Because technically, if you were to work this out, whenever you take a square root, if you remember from Algebra 2, you technically have to do plus or minus. But we don't have to do plus or minus because we're only looking at half the quadratic to begin with. So we don't need to do anything with this. Really, it just makes our final answer a little bit simpler to find. All right, let's try another. If you feel comfortable, pause the video, try this one on your own. But at least we can get this set up. Switch x and y. Okay, so to get x by itself, I'm going to multiply both sides by y minus 2. So I would get xy minus 2x equals 5, because again, I'm multiplying by 5 minus, or y minus 2 to get that by itself. So now I'm going to go ahead and add 2x to both sides, and then I'm going to divide by x. So I end up with 2x plus 5 over x. Now there's a couple of different ways you could write this. If you wanted to write this as 2 plus 5 over x, that would also work. You don't have to write it that way, but that is probably the easiest way, is just to leave it like that. And again, I'm going to write f inverse, just to get in the habit to know what that means. All right, so hopefully you remember this from Algebra 2 as well, but if not, there's actually a way that we can use composition that we did two class periods ago, or one class ago, I'm sorry, in order to determine if two functions are inverses. So what we do with composition, we do two different things. I do f of g of x, and then I also do g of f of x. So if you remember what that means, f of g of x means you take the g of x function and you plug it in for x in the f of x function. If both of these things simplify to just x, that's proof that these functions are inverses. So let's start with the first one, f of g of x. Okay, so I'll rewrite that as f of 1/3 x plus 1/3. So I'm going to replace x in the f of x function with 1/3 x plus 1/3. And the original was 3x minus 1. So we replace the x. Now let's simplify. 3 times 1/3 is x. 3 times 1/3 is 1. X plus 1 minus 1 is x. Okay, so that one works. But we have to try the other way as well and make sure that the other way works. So we'll do g of f of x. So g of f of x would be g of 3x minus 1, which means in the g of x function, I'm going to replace x with 3x minus 1. So I replace the x, and then we simplify. 1/3 times 3 is just 1, minus 1/3 plus 1/3 leaves me with just x. Since both of those things equaled x, yes, these two functions are inverses. All right, let's try this other one. I'll start with f of g of x, which means I'm going to replace x in the f of x function with the cube root of x minus 3. So this would be x gets replaced with the cube root of x minus 3. That gets cubed plus 3. So cube root cubed is just x minus 3. Plus 3 is still there. All I'm left with is x. Now again, we have to try it the opposite way as well. So g of f of x. Okay, so g of x cubed plus 3. So in the g of x function, replace the x with x cubed plus 3. So this is going to become x cubed plus 3 minus 3. Do what's under the root first. So plus 3 minus 3 is 0. The cube root of x cubed is x. So yes, those are also inverses of each other. So again, composition is a way to prove that. All right, so the last thing we're going to look at is something called one-to-one. So a function is one-to-one if its inverse is a function. So that second example that we looked at when we said whether or not the inverse was a function, the first one where the graph looked like this and the inverse looked like this. The inverse was not a function, so the original was not one-to-one. The second one that we looked at, okay, the original looked like this and the inverse looked like that. The inverse was a function, so that original was what we would call one-to-one. If a function is one-to-one, then it will pass the horizontal line test. So very similar to the vertical line test. So let's look at this first one. Okay, yes, this first one here was a function because it passes the vertical line test. It does not pass the horizontal line test. A horizontal line can touch two places. So that means that it is a function, but it's not one-to-one. It also, let's look at this next one. This passes the horizontal line test, so its inverse is a function, and we say that it's one-to-one. All right, so let's look at these examples. We just want to determine whether or not these are one-to-one. Well, looking at this first one, if I were to draw a horizontal line anywhere in this graph, it will only touch one place. So yes, this function is one-to-one. That means its inverse would be a function. But let's look at B. I can draw a horizontal line and touch two places, which means its inverse is not a function, so it's not one-to-one. The second one, it looks like maybe right there, but if you were to zoom in really far there, you would see that it doesn't actually repeat any of those values. So this one does have an inverse that is a function, so it is one-to-one. The inverse of that, if you remember from Algebra 1 or Algebra 2, that's x cubed, so the inverse is the cube root of x. All right, and then let's look at D. Fails the horizontal line test, inverse is not a function, so it is not one-to-one. All right, so that is all we have for today. Hopefully some of this looks a little familiar. If not, just remember, switch x and y in order to find an inverse.